In a slight change of schedule, we're not going to have Bob. We're going to have Adriana Correia speaking from Utrecht University, and the talk's called Putting a Spin on Language. Take it away.
Hi, this is Adriana talking to you from Utrecht, the Netherlands, and I'm going to present work that I've been doing with my supervisor, thanks to Michael Morgat, on yet another way to improve natural language processing using tools from quantum mechanics. So first, I'd like to talk about relative clauses and what they are. So we can see these two phrases, man that bites the dog and man that the dog bites. So in the first case, it's the man that does the biting. And in the second case, it's the dog that does the biting. So what happens when we ask Google to translate this to Dutch, which is the language of the country I'm currently living in? What happens is that it translates to the exact same surface form. So man die de hond bite. So what we see here, relative clauses in Dutch are actually ambiguous. So both readings have the same writing. And well, we could imagine that even though this is the case, Google actually keeps track of what was the original meaning. So is that what happens if we ask Google to translate back? What we see is that it actually doesn't. So it translates both back to the first reading, man that bites the dog, or who bites the dog in this case, because it's a personal pronoun, which is funny, isn't it? Because the most likely reading would even be that dog does the biting. So what's happening here? So to understand this and to propose a way to keep track of which reading was which originally, I'm going to introduce a theory of syntax, Lambek calculus, and a theory of semantics that interprets that syntax based on vector representations of words. Okay, so first for the semantics. We start with looking at verbs and interpreting them as function words. What does this mean? That they take other words that are of a simple type as an argument. And in this case, lips is an intransitive verb, so it only requires one subject. So it has one argument slot as subject. And when we compose them, we find something of type sentence. So if we can merge these two words of these types together and we can prove that it arrives at this type S, then this is a well-formed sentence. Other example is young physicist. So young is an adjective, and an adjective would be a function that takes a noun and delivers another noun. And for transitive verbs, we have a function that takes two arguments of type noun, in this case, student as subject and physics as object. And we show that it is well-formed sentences. How exactly we show? I'll come to that in a bit. Okay, so this is for English. And what happens in Dutch? So for Dutch relative clauses, what happens is that this is a structure with verb final structure. So bite, which is the verb, which is a transitive verb, that is, it requires an object and a subject, asks for both arguments coming from the left, because the language is directional and our syntax encodes that. So in the first reading, dog, the hond, attaches to the object position, whereas in the second reading, it attaches to the subject position. And well, very intuitively, we can see why Google would assume that this would be the translation on both cases, because this is the one that doesn't imply any wiring crossing, let's say. Okay, so to define this more formally, I'm going to introduce the logics behind this composition of types. So this is the Lambek calculus. So first of all, we have an axiom to just declare a word of a certain type. And then we have elimination rules, which is just application of this function of an argument of type A to something of type A returns a B, and a counterpart on the other direction, an artifact of the directionality of language. So even though languages will have different preferences from left to right, all languages will have a fixed type with a fixed direction for certain types of words. And if we generate the functions, then we apply this rule here. And par with the proof steps, we have proofs as programs. So each proof step gives a recipe, a program to calculate meaning in parallel or interpretation of our sentences. We will need to extend this calculus with unary modalities. These are adjoints, and we call them diamond and box, and we can introduce them and eliminate them. And although this is not, well, standards in most Lambek calculus uses, it's going to be necessary to start from the same type assigned to our words of the Dutch relative clause and end up with different meanings that follow the proof steps. And why is that? Because we will need to use structural control for that. So in principle, we might have rules that change the bracketings of formulas if we're looking at the categorical morphisms, or that swap the positions between the formulas. But we do not want to have that in a general way, because we want to have the necessary and sufficient rules to derive grammatical sentences and phrases, no more, no less. So what we do is we allow associativity and commutativity only for certain mark types with relative positions to other formulas. And in the previous presentation, this will be the form that it takes. So now what is the type of D? D will have this type here that will have here for NP. Will modify NP, will decorate NP. This diamond box. Diamond will indicate that the controlled, the structural control can be applied, but it's not necessary that it is applied, it just can be applied. And because these are adjoints, in effect, this will accept an argument NP. Okay, so these are the types that are assigned to our words, and starting from the same types, we can derive both readings. In this case, we do not apply the structural control, and in this case, we do. Okay, so par with the syntax, we want to have an interpretation. We are going to use a distributional interpretation. So the first incarnation of this was to assign to basis words such as nouns or fragments that have basic types such as sentences, just a vector, and functional words would be interpreted as linear maps. Underlying that would be a vector space that would formalize and generalize its construction. Next, people started working with density matrices to represent basic words and completely positive maps for functional words. We are going to use that as well because it has shown to give good results for ambiguity of certain words, of the meanings of words, lexical ambiguity. But we are going to introduce it with a twist. We are going to consider the possibility that the bases that are describing the underlying vector spaces are not orthogonal. And this is very nice because it will allow us to include the notion of directionality of the syntax also in the interpretation. The other thing that we are introducing is tensoring this spatial part, which is an analogy on how states of particles in three-dimensional world are described, with a spin part. It's going to be in this spin space that the rules for introduction and elimination of unary modalities, as well as the structural control rules, will be interpreted. So instead of messing with this spatial part, it will act on the spin space, keeping track of which derivation took place. So if we want to translate back, we know what was the intended original meaning. For that, we will have a morphism that will send each syntactic type to the distributional interpretation that will be formed by the tensoring of the spatial part with the spin part. Notice that each spatial part will be a counterpart of a syntactic type, where spin space will be just one. For example, we will use a two-level spin space, but in principle, it could be any dimension. Okay, so what I was talking about, non-orthogonality. So imagine that the vectors that are describing our words are not described in a flat space, but instead they live on a curved manifold. What do you do with that? What we can do is map it to the tangent manifold on a point, say the origin of that vector. And we can do that with other vectors that live on this manifold. And then we can take the inner product on this tangent space. That's this function here. That's the metric. Now, the metric also serves as a map between the dual vector space and the vector space. And the dual is the cotangent space. And we are going to use this property to talk about directionality. First, we're still in density matrix formalism. So we say that the density matrix generated by the underlying vector space V is V tilde, formed by V tensor V star, the dual vector space of V. And the elements are described in these spaces that is dancing between a cat and a bra, but with these indices down that represent bases of the underlying vector spaces. And as is common in tensor calculus notation, the main vector space will be described with indices down, and the dual density matrix vector space will be described with indices up. And then the metric comes when we ask for the inner product between these two vectors. Then here we'll have a component of the metric tensor, while for these we will just have a delta. That means that if we contract always with elements that have an opposite height, let's say, then the contraction will not leave any leftovers. Whereas on the other hand, if we do contract with something on the same height, it will leave a metric element. So we are going to interpret our syntactic types for the spatial part in the basic types for S as S tilde and for NP and N as N tilde. Our slash types will be interpreted as the spatial part of a tensor, the dual spatial part of B. And for the other slash, we will have this relative position. So when we look at the elements of these spaces, now we have the elements describing them, the tensor elements describing them with different heights. So when we ask for a contraction with, say, something now of type B, it will have elements down, as we see here. And that means that the contraction will not leave G component, and then the contraction has been made in the proper way. So we have effectively introduced the notion of directionality in the interpretation. The spatial part interpreting our types is this. For our Dutch relative clause, we see again that it is possible to contract this N with either one of these dual N's here. This is what gives us both readings. And now we are at the interpretation level. And we see how that goes hand in hand with the syntax. Okay, now for the unary connectives. The interpretation of the unary connectives at this level will be the tensoring between the spatial part of the unmarked type A, tensored with an operator on the spin space. So while both will live on the same space, the particular operators interpreting each unary modality will be different and specific. And let's look at the candidates. So one candidate is quantum measurement. That is to apply a certain measurement to a density matrix state rho. That will give me the value A. So if this is an eigenvalue of operator M, then MA is the operator formed by the tensoring of the eigenstates corresponding to that eigenvalue. Of course, this is normalized by the trace. That is the probability that the value A actually is the outcome of this measurement. So this is one option. The other one is evolution. A unitary operation then is applied on density matrix state rho and gives me rho star. This is an evolution of a closed quantum system, while the quantum measurement is talking about an open quantum system. Okay, so because we are looking at our proofs as programs, we're going to interpret each proof step in our interpretation spaces. Axiom will be interpreted as a tensoring between the spatial part. Oh, I think this is up. The spatial part and the spin part here. Now, the elimination of slashes will be on the spatial part, the partial tracing at the space that is being contracted. And for the other direction, it's the partial tracing with the symmetric states reversed. For the spin part, remember there's only one spin space, so we're taking two spin states and converting them into one. For that, we're going to use this operation that has been used in the literature of quantum NLP before, but basically it takes this dense symmetric state and it calculates the square root. So because this is a positive operator, this square root is unique, it's the principal square root, and the square of this object here will be just this row back. So this is unique, and in particular, if this is a pure state 0 or 1, if we align it so, then this whole thing will be again that pure state. Okay, now for the unary modalities and control commutativity, first for the introduction of diamond, we will interpret this operator as a projection onto the lowest eigenstate of a certain operator that for us will be the spin measured along the z direction. So here the state 0, this one here in the block sphere that represents the two-level spin space. For introduction of blocks, we will have a unitary operation that in our version is just simply identity. And for control commutativity, what we're going to do is apply a raising operator. That is, if the dense symmetry is on state 0, it will raise it to state 1. In general, it just generally raise it indexed on the eigenvalue. But for us, it will top at state 1. So remember that only one of the readings depending on this structural control. So the first reading where structural control is not used will remain on 0 state, while the second will be sent to the 1 state. And this is how we're going to distinguish them in broad strokes. But this is a little bit more involved in that, because remember those nice triangle diagrams that I was showing? Well, they actually correspond to these very nasty proofs that are constructed with the proof steps that I gave you. I'm not going to go in detail over them, but just keep in mind that each one of these has to be interpreted with the distributional interpretation that we gave both in the spatial part and in the spin part. So after some 8 pages of calculations, we arrive at this nice result. So in our distributional interpretation, we have the spatial component of the reading. So we see here that this indicates that these have been contracted in object position and here in subject position. And it's while D attaches to the subject position that then men comes through it and also attaches there. While for the second reading, it's the other way around. So Hond attaches to the subject position and men comes to the object via D. While both of these are in the noun space, they're just values, right? If we would have values for these density matrices, these would just compress and I would just have one volume in this space. But the result that comes from the spin space would allow us to distinguish clearly which one was which and to keep that information at the interpretation level, which is pretty nice. So now if Google wanted to translate it back, then it could just look at what value is there on the spin state. Finally, the full interpretation of this Dutch relative clause would be the direct sum of both readings weighted by the likelihood of each one that we would also hope to extract numerically. So you see that this is a compromise between having some numerical values here and following the syntax and interpreting it hand in hand in this spin space so that we can arrive at this result. Okay, so this is what I had to tell you. So the take-home message is that diamond and box can be used for control manipulation of phrase structure and word order, that we can expand the relationship between vector representations of words with the metric G that is then used to keep information about the directionality in the interpretation space. And we can expand the amount of information that we keep in our distributional representations of words if we increase it with a spin space that, as I said, could be of higher dimensionality, which we hope is the straightforward solution to multiple ambiguities. If they are of the same type, we would just use the control commutativity more times. So with a bigger spin space, that would mean that the raising operator would be allowed to raise the spin state further. But we also want to see if this works with other applications of modalities, such as dependencies and the scope of the application of certain functional words. And finally, the next step is to extract numerical values for the metric and density matrices and the probabilities of these two readings. That, well, intuitively, you might have a feeling of which one is more likely, but how much more likely is it? Okay, thank you. Are there any questions?
Thanks very much. Thanks for that nice talk. People are typing in the Slack channel, but can I ask a quick question? So you're using basically a full quantum mechanical treatment of this spin space, right? The underlying object is the block sphere. Yeah,
Yes.
you don't see superposition really coming into it, right? I mean, you've got this direct sum, and so you could just have a classical extra degree of freedom, right?
Right. The nice thing here is that we are really able to extract these outcomes from interpreting each ruling, following the interpretation to the conclusion. But yeah, it would be really nice to have a superposition. But because we're starting already with density matrices states, that's a little bit harder to obtain, I would say, and also to find the meaning of what that superposition would be exactly. Because now indeed this is a classical superposition, I would say, that distinguishes both readings.
Oh, okay. Because you're using density matrices, you want to introduce another vector space with which you can take a tensor product rather than like a classical variable saying.
Yeah. And we hope that while this now seems classical, that if we extend it with more modalities, so now we only have one diamond and one box, but well, in the syntax, sometimes you need more. So maybe you can have other operators that correspond to other diamonds, say. So those might interfere nicely.
Oh, okay.
Yeah.
Okay. Right. Oh, there's a question.
Please.
So Teacher One says, hi, the extension of Lambek calculus you are presenting allows displacement. How does it differ from combinatory categorical grammar?
You mean in here? In here, for example, possibly.
Hopefully there could be a reply in the Slack.
Yeah. So these are well, there are different ways of presenting the same calculus. However, if we would be working with fully with the categorical morphisms and with application co-application, we would also have to go through the cut rule, which is something that we do not want. I don't know if that's the question.
Okay, yeah, I don't know. There's been no reply in the Slack, but there are a couple of other people typing. Okay. Oh, someone wanted to ask the same question I asked. Okay, that's fine. Alexei Toomey asked about polarity items. So, can this framework be used to give a semantics to linguistic polarity items?
That's a good question. I haven't looked into it. So here, these are really inverses of. So in interpretation, things are inverses, and I don't know if the polarities would really cancel each other. So I wouldn't know. I wouldn't know.
Okay.
I understand the question, but I don't have a good answer. It's something interesting to look at.
Okay, I've just seen that there's a lag of a few seconds between this call and what's on YouTube. Okay. So probably people are responding. Yes. Okay. There are more questions. My question is: if we have more than 2 readings, could we still use, let's say, high dimensional spin spaces to distinguish them? So instead of it just being 2, it could be more.
Yeah. So that's the proposal. If the ambiguities are generated in the same way, in the same structural way, and if you need to use this control commutativity, then the interpretation that we are providing will work. For example, dog that bites, I don't know, that runs. And in Dutch, imagine that this has many readings. Then depending on the application of the number of applications of the structural rules, then you could start by projecting on the lowest eigenstate and then increasing the states and distinguish the readings.
Okay. But this is obviously distinct from introducing more operations, right? You would generalize these operations that you have, the diamond and the square. Yeah.
Yes. Yeah, in looking at other applications, we might need to tweak a little bit these particular interpretations, but we really believe that this is the starting point to do that.
Okay, brilliant. I think if there are any more questions, you can go and answer them on the Slack.
Yep.
But in the meantime, I think we'll have a second round of applause. And
Thank you.
Thanks for agreeing to do this for the switch at short notice, Adriana. It's appreciated.
Yeah, thank you for just putting me on earlier. Than I wasn't nervous or anything. I just did it.
Brilliant. That was good. Okay.
All right.
Thanks very much.
Bye.
Okay,
Thank
bye.
you.